Hey class, today we're going to continue on with Chapter 5 and we're going to cover Section 3 titled Atomic Emission Spectrum and the Quantum Mechanical Model. Now the quantum mechanical model we have talked about in previous lessons, so let's review. The quantum mechanical model describes the allowed energies that an electron can have, which is similar to the Bohr's model, and how likely or the probability it is to find an electron in the various locations around the nucleus of an atom. Now remember, these various locations, usually we call them orbitals. So usually we have energy levels, and within energy levels we find orbitals, and within orbitals we find electrons. Now electrons are in these different levels depending on how much energy those electrons have. And I know down below this is a picture of the Bohr model, but it gives us the best visual representation of what's happening. One thing to know about the quantum mechanical model is the reason it was supported, and also the Bohr's model was supported, is because it explained why we saw colors of light being emitted whenever energy was applied to a certain chemical, such as if we heated up copper, it showed green light. If we heated up potassium, it showed purple light. So let's talk about the nature of light before we get into how the quantum mechanical model is supported by this. By the year 1900, there was enough experimental evidence to convince scientists that light consisted of waves. And so there are a couple pieces of information that we have to know about a wave. And these three definitions are definitions I do kind of expect you to understand. The first definition is the amplitude. An amplitude of a wave is basically just the height. And it says from 0 to crest. Now 0 just means this line. This line right here is 0. This top part is going to be considered the crest. So from here to here, this would be considered the amplitude, or over here it shows the arrow. The next definition is wavelength, and this is probably one of the two most important ones to know, so I'm just going to go ahead and start it. A wavelength is actually represented by the Greek letter lambda, so it kind of looks like a little line with a squiggly. I personally remember this because it looks like a wave. This is the distance between two crests. So from this top of this crest to the top of this crest, again, this little sign right here means wavelength. Again, it looks like a wave. The next most important term, so I'm going to go ahead and start this because wavelength and frequency are the two most important ones, is frequency. Frequency is represented by the Greek letter nu, so it looks like a V. This is the number of wave cycles it takes for a given unit of time. So if you say this was 1 second, and then you said right here marks 2 seconds, how many wave cycles did I see? So 1, 2, 3, 4, 5 wave cycles were given. The unit for frequency is going to be hertz, which can be written as 1 per second. So hertz or 1 per second. Now the reason I said wavelength and frequency were the two most important is because the product of frequency and wavelength actually equals a constant known as the speed of light. So again, we use the equation C equals wavelength times frequency. One thing to know is C is going to be our speed of light. This guy is wavelength. And here we have frequency. Now I'm not going to have you solve for these, but it is important to kind of understand what this equation means and what it's trying to tell us. And one thing that we do need to understand, and I'm going to underline and basically star, is the speed of light is always going to be the same no matter what light we're seeing, whether it's blue light, green light, microwave radiation, or X-ray radiation. The speed of light is always going to be 2.998 times 10 to the 8th power, and then of course speed's unit is meters per second. Now let's kind of break down this relationship that we see in this equation. One thing that we should understand is that frequency and wavelength are inversely proportional. And all that means is as wavelength increases, your frequency actually decreases. You could also say wavelength decreases. That means your frequency increases. So it doesn't matter which way you say this, they're always going to run the opposite way. So we have two pictures here. Here, this chart has low frequency because it has one, basically almost two waves in this chart. And then you'll notice that my wavelength, which is right here, is pretty long. But if we look over here on a high frequency chart, where we have about 1, 2, 3, 4, 5, 6-ish wavelengths, frequency waves, we have a very short wavelength. So that brings into what counts as light. Light actually is going to consist of electromagnetic waves. There are different types of electromagnetic waves, and we call this electromagnetic radiation. This includes things like radio waves, microwaves, infrared waves, visible light, ultraviolet waves, which you guys probably know as UV radiation. That's what gives you your sunburns, X-rays, and gamma rays. No matter what ray we're talking about or waves we're talking about, all of them travel at the speed of light in a vacuum, which is 2.998 times 10 to the 8th meters per second. Here's a chart that shows the electromagnetic spectrum over a broad range of wavelengths. And notice that visible light, or the colors that we see, is only a very, very small part of this chart. One thing I want you to know is we can see the wave happening here. So over here where it says radio waves, notice that this side tends to have a low frequency. And notice these wavelengths are going to be pretty big. So they have low frequency but long or big wavelengths. This fits as one goes up, the other goes down. Over here near our gamma radiation, we're going to see here that here we have high frequency, but that means we have short wavelengths. So I know that's hard to see, so I'm spelling high frequency, short wavelengths. Same thing happens with our visible light spectrum. Now, visible light, if you've ever been taught the phrase Roy G. Biv, stands for the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. Red is going to have the longest wavelength because it's closest to the left side. Purple, or that violet indigo, is going to have the shortest wavelength because it's closer to the right-hand side. Now, why do we care about light, and why do we care about this electromagnetic spectrum? Well, whenever we take light and we pass it through a prism, which right here in this image is a prism. If you've ever seen the front of the Pink Floyd album, they do the same thing as well. You will see that this light will actually separate into the colors of the rainbow, and we call this separation of light a spectrum. White light, such as sun or an incandescent light bulb, produces a continuous spectrum, and all that means is that this rainbow is continuous. There are no blanks, cut-off spaces, or anything cutting it up. However, if we took elements, they do not produce a continuous spectrum. Say I put elements into a bulb, I captured that element, and I gave it some kind of source of electricity and shined a light on it, and then we took that light and passed it through a prism. Again, it would not be continuous spectrum. It would only produce certain discrete lines. And these lines are specific to an element that is being shown. And this is because these are the different frequencies that these electrons are giving off when they jump down energy levels. And we call this the atomic emission spectrum. Again, it's a spectrum because it shows color, atomic because in atoms showing them off, a specific element. For example, helium, if we were to pass it through a prism, shows these discrete lines. And one thing you have to understand is no two elements are going to have the same discrete lines that are produced. So these distinct lines give proof to the idea that electrons exist in these distinct levels. And no two elements are going to have the same number of electrons in these specific energy levels. We saw this when I asked the idea. I gave you the electron configuration of an element and you were able to tell me which element it was. An atomic emission spectrum is actually unique to a given element, and this is how we know what elements make up our stars. So here, the top one is a continuous spectrum of white light, but let's say we had this element sodium. It only produces this atomic emission spectrum. Notice hydrogen produces a different, calcium's different, and mercury's different. All of these atomic emission spectrums are different. So what actually causes the atomic emission spectrum? Let's kind of talk and dive into a little more detail about what this actually is. And what we need to understand, and what we've been talking about this entire section, is that atoms absorb energy. Now, they can absorb energy a lot of different ways. We can heat them up. We can shine a light on them. And when they absorb energies, those electrons move to higher energy levels. But they can't hold on to that energy forever, and eventually these electrons are going to have to release that energy, and they lose it. And when they lose it, they give off and shine off light. So when an electron is at its lowest possible energy, which means its normal state, we say that this atom is in something called a ground state. A ground state would be its lowest occupied energy. So let's say if an electron belongs in energy level 1, its ground state would be 1. Now, these electrons can actually be excited and absorb energy and raise to other energy levels. So this electron in energy level 1 can actually skip to energy level 2, 3, 4, 5, or 6, depending on how much energy that it gained. And we call this jump in energy levels the excited state because it gained energy. It's kind of like a kid. If they gain a lot of sugar, they get really excited. And remember, the amount of energy or the quantum of energy they gain has to be the same amount of energy that they release when they drop back down those energy levels. And this amount of energy takes the form of a specific amount of light, and it ties to something known as energy. So this amount of energy that electrons give off is tied to what we know about frequencies of light. So actually, I'm going to go back up to this picture. Notice up here that over here we have red light. Red light has a different frequency than indigo light. Green light will fall under a different frequency than yellow light. So we have to tie this all back to energy. And I'm going to go back to the slide here in a second, but what I really want you to understand about this picture is notice here they categorize this red light as having low energy and indigo violet light as having high energy. So how do we actually know that? One thing to know is that when light is emitted from an electron moving from a higher to a lower, and that's important. So I'm going to go ahead and start that. It has to be high to low. They release energy. We need to know that frequency is directly proportional to energy. And all that means is if frequency increases, energy also increases. Same thing if we were to reverse it. If we said frequency decreases, energy would also decrease. They are related in that way. And there was actually an equation made by German physicist Max Planck. He mathematically showed this being proportional, and he came out with the equation E equals H times V. Now, E stands for energy and V stands for frequency, but we have to kind of understand what H is. And H stands for something called Planck's constant. It is a constant, which means it will never, ever, ever change. Again, E stands for energy. H is Planck's constant, which is 6.626 times 10 to the negative 34th joules times second. And then V, we already learned this variable. This is frequency. So this ties together energy and frequency. So here it shows 3 groups of lines in a hydrogen spectrum corresponds to the transition of electrons from higher to lower. For example, if an electron was on the 7th energy level and it dropped down to the 1st, it's going to release a certain amount of energy, and this amount of energy corresponds to more of a purple or indigo violet color on our frequency scale. Here, if we drop from 7 down to energy level 3, you're going to see more red light be given off because that's not as much energy. Red light tends to be low energy, purple tends to be high energy. Notice this line right here is a slightly different color because it falls kind of in the middle. It has a middle amount of energy. So in a hydrogen spectrum, which of the following transitions will produce the greatest amount of energy? Well, a couple things before we answer this. We have to understand and remember and think back to our energy levels. Notice from 1 to 2, that's a big gap. That means I have a lot of energy. From 2 to 3, notice the gap's smaller, so you don't need as much energy to jump from 2 to 3. Again, here we have 3 to 4. You don't need as much energy to jump there. So if we look at our jumps, we have energies level 2 to 1, 1 to 2, and 4 to 3. Again, you're going to see the biggest jump on the inside. So let's look at these in the picture. We have 2 to 1, then we have 2 to 3, and then we have 3 to 4. Notice our biggest jump is 2 to 1, so that is going to be our answer. Now that won't always be our answer. What if I had the options n equals 6, 2, n equals 1? Notice that if we look at this picture, 6 to 1 is a bigger jump, so this releases more energy. So you really got to think about how big is that jump. And again, I'm going to finish out this lesson by again going back to this picture. If they have a jump that releases low energy, we tend to see the frequency of having red light. If we have high energy, we tend to have purple light. Again, I also want to bring back this idea that frequency and energy are directly proportional. Again, we see high frequency, high energy. Here we see low frequency on the left. That means we have low energy on the left. So these are just some correlations and things to kind of understand. It's more conceptual. So if you have any questions, please let me know. But this is the end of the lesson for today, and I hope you guys have a great day.